You lucky people, we have, of course, saved the best till last.
Of course.
So if you could all sit down and open your ears for Charles Nutter. And co.
And co.
All right. So we're going to get right into this. We planned for a little bit longer than 25 minutes, so we'll rail through it. All right.
So I'm Tom Enabo.
I'm Charles Nutter. We've been working on JRuby for, what, 15 years
Over 15
now?
years apiece.
Yeah, crazy.
For people who don't know, JRuby is just another implementation of the Ruby programming language and runtime. We recommend it. But why did we make it? We made it to exploit some features that CRuby doesn't have, like the ability to execute concurrently on native threads. We can access Java libraries from a Ruby syntax, and pretty much get all the good stuff that Java has to provide. We run fast. But we have a problem. Startup time is not where we'd like it. It's slower than CRuby. Ruby is constantly going type commands on the command line all the time.
That's the whole development process, is all command line driven. So.
And for as long as we've been doing this, we've been trying to solve it. Oh, your keyboard sucks. So here we're executing the simplest program. We're going to evaluate the FOSDEM 1. By this period, load 415 Ruby classes and modules. Over 300 of those come from Ruby source that we have to parse and then interpret. If we actually go under the covers, now we're loading over 6,000 Java types, and 5,000 of those are from JRuby. Our internals, method handles,
interpreter, instructions, all of that.
Ruby's also very dynamic, so we can't look at a source file like this and go, oh, require normal. Oh, we want to load a file called normal. Someone might have overridden that. Could be something else.
Could be a different path.
We've tried speculatively trying to load these things in the background, but we don't fully know. It's also a path-based language. So when we do require normal, we're going to just do a lot of stats.
So basically, it's like if Maven libraries were all distributed so that they all have their own loose file path on the file system, and then you have to search through all 3,000 of those file paths to find the one file that you're looking for. So that's how it works in Ruby, pretty much.
It's a problem.
There are efforts to try and cache some of this information, but it's still early for that.
But of course, when we're doing startup, almost everything we're loading at this point is only going to get called or executed once, and in Java, that's going to be stuck in the bytecode interpreter. Not many things are going to actually make it to C2, and a good way of illustrating this is with the graph. So this is E1 again. With CRuby, it takes almost no time. When we run it, this is an older slide, but it was about 10 times slower when this was made. Now, as an experiment, we wrapped invoking a Ruby runtime into a loop and then timed it. So at the 10th iteration, we're starting to catch up to CRuby, and by the 50th, well, we're pretty much done and we're beating it. So if we could get this performance right away, we wouldn't have to have this talk. Again, this is kind of a duplicated slide doing the same thing. Gemlist is an important command for us because Ruby Gems is the packaging system for Ruby.
So it kind of shows that as we're doing a little bit more work, CRuby is going up, but that ratio doesn't change a whole lot, how slow we are compared to them. So a little bit more background, other implementations. Of course, we're talking about CRuby or MRI here, the standard C implementation. The peak performance is low. It's the lowest of the available Ruby runtimes, but everything starts out hot. So the parser starts out hot. They have a very lightweight bytecode compiler and interpreter, and so they get up and going fast. They're loading all of those same Ruby files and defining that same number of Ruby classes, but they're doing it at about 0.1 seconds.
Oh, okay.
The other one that is interesting right now, actually I don't need this, I have this. The other one that's interesting right now is Truffle Ruby, which is a Ruby implemented on top of Truffle and Graal VM. It's a very interesting project. They show very good peak performance, but they also have this same sort of startup issue, even more so, just because of the way they're designed. They do a lot more interpretation at boot time, so they're solving it in some of the similar ways. We'll talk a little bit more about them later.
All right. Oh, and we have a few more minutes. So.
Okay.
Okay. Yeah, so we're going to talk about some stuff we've done in the past. Some of this has stayed and some of it has went. Towards the beginning of the 2000s, we had a simple AST interpreter. So we just parse that into a stream of lexical tokens and build an abstract syntax tree. The interpreter would bounce around. What's that? Oh, that should have been removed. And startup was okay back then. Ruby was a much simpler environment. It wasn't loading as much stuff. And we might have still been 2 or 3 times slower, but 2 or 3 times slower when it takes like 1.6 seconds, it's not really a big deal. The first optimization that's ever happened for startup happened before either one of us started on this project. They would go and save the Lexer tokens to a file and then reload it. Back in Java 1.4 days, this was actually a pretty big optimization. But by the time we supported Java 5 and up, we had optimized the Lexer and parser, and it got down to like 3%. And then we're like, why are we supporting this weird serialization format? It's just not worth it. A bit more time passed, and then the first JIT compiler came, and this was about the same time that Ruby was also improving its performance, so we were kind of having that performance arms race, or staying ahead of it anyways. But this doesn't have any effect on short-lived processes, because by the time we actually JIT something, the process is already done.
Right, and this is, to make it clear, this is a JIT from our internal instructions to JVM bytecode, which then the JVM would eventually JIT. So we're way, way off of that tail of getting any sort of optimization startup-wise.
But there was one benefit. If you loaded a huge application, things started to warm up, and you started to get the payoff, and then the startup time of a really long process got faster. Well, if you can go and compile everything to Java bytecode, why not compile everything?
Mm-hmm.
This experiment didn't really pan out too well. With the verification on it was like 10 times slower. It was really, really slow. If we disabled it, it still was slower than just parsing Ruby. So, well, Charlie's going to talk about that more later. In our race for performance, we created our own internal representation with a virtual instruction set. We can do things like inline a method with a closure and inline that back to the call site. But because we're doing this extra building, we actually made our startup time worse, which sucks. But again, if it was a really long process, we continue to get a little bit faster in that case. Well, we realized that the AST tree in memory was quite a bit smaller than our IR, so we decided to get lazy, and until the first method was called, we didn't actually build the IR itself. It was mostly a memory optimization, but it did actually improve startup a little bit. We're back to serialization again. Google Summer of Code project, someone spiked this, and we really were hoping it was going to be magic.
Turns out it's not,
It's
unfortunately.
not. We'll be talking about serialization more in this talk.
And the parser and the compiler end up getting so hot that it really doesn't make any difference compared to serialization. We still create all the same number of IR objects in the end, so.
Our most effective optimization we've ever made for startup time is to disable everything. So
just turn it all off.
we only use our startup interpreter. We disable C2.
To this day, this is still really difficult to beat C1 on just everything. It's always the fastest.
But now we have to worry about people passing --dev into their production environments. So
Yeah.
it's not
Sending us
ideal.
benchmark results that aren't what they expected, and I'm like, it's just this client server all over again.
But you can see doing this gem list again that it's about 33% faster.
Yeah.
So it was a pretty big win. In the past, we played with native compilers. Excelsior Jet's the one that I had some experience with, and it got better in --dev, but again, it's one of these things where we didn't really want to go that extra step. It's something else to support, and then it was also a company. May they rest in peace. But we'll talk about native compilers later too.
Okay, so Well, startup experiments. I was doing pre-booting, right?
You got a mic.
Yeah. Oh, right.
Do you want to sound twice?
Yeah, no. I want everyone to really hear me. Okay.
Do you want to sound twice as good?
Okay. I'll use this one. It's fine. Yeah. So now we're going to go over some of the current experiments that we've been working on, things that are still sort of active projects. We'll just jump right into those here. So pre-booting, this is similar to what like a Scala compiler or Gradle build will spin up a background process and then you throw more work at it. But we have some specific things for Rails and people do use those, but we've tried some general purpose options. The first one was Nailgun, which you start up a background daemon JVM. And then you continually throw new operations at it. They run in their own class loader. They're isolated as well as class loaders can isolate things. But it really didn't work well with the way Rubyists write these applications. They would spin up threads and expect them to go away when they're done. They would allocate resources and maybe walk away because it's going to be a short run process, stuff like that. So a lot of resource issues never really kind of panned out. Drip is a little bit better. Not a lot of folks know about Drip. Drip basically will just start the next JVM. So you run a command, there's nothing available. It'll start the one you're targeting and a second one to get ready for the next command. And you can have a stack of these, so you can have up to 5 or 10 or whatever. And then as you throw more commands at them, you've already got a JVM up and going. But it's also got to do a lot of TTY juggling to hook you up to that process correctly. And these instances in the background will eventually pick up stale code, and you'll have to say, oh, wipe out all of them, and then I'm back to slow startup again. So kind of more problematic than it was actually worth. We are interested now in using the checkpoint and restore stuff on Linux. Some folks at Red Hat are experimenting with this, but I think it's still kind of early days. We haven't had a chance to play with it much yet. So that's kind of where we stand on pre-booting stuff.
So we revisited serialization recently, and one thing that we always wanted to do was lazily load the instructions, just like we were being lazy with the methods with IR build versus AST. But there was a weird artifact in our implementation that we solved a week or two ago. So now that works. So let's see how that's turning out. I don't know why these are built out. So here, if we look at old serialization to new serialization, we got a good bump by being lazy. It's fine. And it's actually now went from being a little bit slower to a little bit faster. This is only 20 gems, so this is doing virtually no work. It's kind of a worst case of being something useful. But now if we go to 2,000 gems, which happens to be my personal work dev, one more. We can see that it still improves and it still holds true, but it's getting a little less interesting. So is this worthwhile?
Right. At this point, enough stuff starts to jit at the JVM that we don't get as much of a gain off of it, we suspect.
And so on this last one, it's going into Rails console. This is doing multiple invocations of Ruby. And you can see that serialization really isn't playing any role at all here. So there's a different issue with startup there, but this really makes us not know whether we want to continue this or not. But when we came to Europe, I noticed that there was a constant pool index that we weren't using in our format. So I'm like, oh, let's add some constant pooling. So I'm saving symbols to a pool. This prevents having to go and decode a bunch of bytes for the symbol name and its encoding, and it doesn't have to look up in our global symbol table. And basically, we just have a new box here. It just got a little bit faster. So it's encouraging because there's a lot of other stuff that we could put in there. I'm just going to pop through these quick. And you see the same approximate ratio. So I'm always one off on that. So as you'll see later on, there's other things that might be more exciting than this.
Yeah, there's more to do here too. This is still doing a constant pool per scope. A constant pool for an entire file would make some sense. You try and share those symbols as much as possible.
Yeah, we're going to keep chipping away, and it might become worth it.
Right.
Because it works really well for really short commands.
Mm-hmm. Okay, so returning back to the JVM bytecode compiler, because of the how much it didn't help us in the older version of JRuby. When we went to our 9.x series, we thought we won't even bother with it. We wrote a new .class compiler that, well, all it didn't actually compile bytecode. It just took the serialized IR format, stuffed it into a bunch of constants in the constant pool, and then when you boot the class up, it just deserializes the IR and starts running it. So it was a clever way to get a .class without actually emitting any bytecode. But we wanted to revisit actually emitting JVM bytecode, doing the compile ahead of time. So normally the bytecode compiler is used as a JIT. We've used this same call threshold for years, and it's mostly served us well. If a method gets called 50 times or a block gets called 50 times, then we will turn it into JVM bytecode, and eventually the JVM will continue to optimize it from there. But it also could certainly support compiling an entire script. One of the things we learned was that a lot of people love to benchmark stuff at the root of the main file that they're running. So if we don't compile the entire file, you'll get a loop that won't run. We don't have any on-stack replacement and stuff. It will never actually optimize. So we always compile the target script completely. Expanding that to the rest of the files that are loaded was not a big leap. So goals for this, obviously, JRuby and JVM initialization are about the same. We're not going to be able to do much to reduce that cost. But hopefully we can get rid of the reading of the file, parsing it, compiling the IR, optimizing the IR, interpreting it. We can launch ourselves straight into the bytecode execution. Maybe reduce the number of JVM classes, probably reduce the amount of heap used because we don't have all of our IR stuff that we have to stand up. And we mostly will get to the bytecode eventually anyway, so it's kind of wasted extra space. But unfortunately, it hasn't worked out as well. We kind of expected that it would be the same thing as we had seen before. So here's just some output from these. In the normal JIT mode with running JRuby, you'll see only the target script, the main script, actually compiles ahead of time. Everything else at runtime, it'll eventually compile once it's been hit enough. Down on the bottom, just change the flag, add a -x+c, which forces every script to completely compile before it starts executing. Then we can see lots of scripts come through. If we combine this with the new AOT mode, which is compile cache classes up at the top, turn on some logging, then we get the whole list of the scripts that are being pre-compiled, dumped into a cache directory, and then the next time they can be loaded directly from the class files. So does it work? Well, it turns out that we're dealing with a tremendous amount of class files here, as you would expect. Just generating a piece of a Rails app, like generating a blog post, the typical blog post thing that people do, produces over 1,200 class files. It's loading at least 1,200, 12 to 1,400 Ruby sources. Those all get dumped into giant class files. 80 megabytes of classes as a result of this one Rails command. And then almost none of this JITs. So we're loading all of this bytecode into the system, running through it once, and then that's it. We don't run it ever again for a short command. So the first thing that I started doing to try and explore this was to trace the actual bytecodes that are being executed. I don't know if anybody's played with this. This is a lot of fun to look at. If you run on the debug build with the trace bytecodes option, you can see all of the bytecodes as they're executed by the JVM's bytecode interpreter. If you want to see them after if you want to force it to not JIT, you'll see all of whatever would run. But once they JIT, normally they will not show up in this trace anymore. So it's a good way to see what cold bytecode is executing, how much a cold bytecode is executing. I'm using Claus's ByteStacks tool here, which you will take that trace bytecode output and it will turn it into a flame graph of your application. So you can see where most of the cold bytecode is executing. Yes, so we're looking for cold execution mostly here. So here is cold bytecodes for -E1. This is split up in JVM initialization, which is the Java part of the modules that first runs to get things going. The base JRuby, which is defining all of our core classes mostly. Loading up JRuby libraries, which is Ruby gems and any additional plugins and whatnot you've got. And then other is just additional JRuby stuff like setting up our native access layer and things. Not really bytecode sensitive, it's mostly callouts to native code. And that's just E1, just the hello world. And you can see that with the cached bytecodes, we're actually running more cold at this point. Rather than getting the gain that we hoped, where we would get into hot code faster. Hot for us is actually cold for the JVM, so it doesn't give us much of a gain. Similarly on gem list, we can see that the Ruby libraries portion and the actual command being executed, gem list, now they have more cold code. They actually slow things down generally. So I went back and looked at this and realized that we were still using a lot of invoke dynamic in a whole bunch of bytecode that only ran once. That really ends up being a waste of time, because all of the bytecode to bootstrap these call sites, all the Lambda forms that are inside method handles, they would all execute through one time and then never be run again. So they'd never JIT. We really saw this if I turned -x int on. It would use a tremendous amount more bytecode because of all those Lambda forms that just keep churning and churning and churning and never turn into native code. So did a modification of this for AOT mode that basically uses no invoke dynamic at all. It's a great feature for us. We love it for peak performance. For cold execution, it is really not that great. There's a lot of issues trying to get stuff to run at cold. I know there's work to try and get Lambda forms and method handles and whatnot to compile in with JLink and stuff. We haven't started playing with any of the work being done there. So the demos I've got here, the results I have here, still are using invoke dynamic for constant lookup, but almost everything else is just using the equivalent bytecode with a little bit less dynamic, a little bit less optimizable, but less cold bytecode to run. So we did get a good reduction here. This is just a very slight reduction from the original cached version. More interestingly, in the case of running a larger command, now we actually start to see that we are running fewer cold bytecodes, and we do get a little bit of a boost from pre-caching that. So we can shrink the size of that bytecode, maybe emit less efficient, simpler bytecode for the class bodies, for the script body, but then use invoke dynamic for the methods and blocks that are called a lot. I think we can get a kind of a happy medium between those two. Okay, so all of these things combined, we've been playing with interpreter modes and JIT and AOT, and then there's all these JVM flags that are coming up and other options. So we wanted to try and assemble a bunch of these together just to see what the best startup we could get with all of our current tricks. So here, this is gem list with just 20 gems, so a fairly small Ruby command running. Here is our original --dev result. Here is throwing appcds at it. So this is helping us. All of those JVM classes we're loading up. It manages to trim some time off of there. This is with the lazy serialization. So that's the serialized IR. Now we're kind of getting a similar gain, but lost a little bit of time. 1.71 here is using the bytecode cache. So again, the AOT to bytecode is just not really a win for startup in any way that we've found so far. And then even appcds with our pre-cached code, it's still just too much cold bytecode executing. So it's not going to get us the startup that we're looking for. But we can do other things with it later. Here on a larger example, a gem list with 2,000 gems, and it has to read through all of them. Here's our dev. appcds gets us there. With the lazy serialization is slightly better than that. And then we start to see that the cached bytecode does have a larger effect with a long-running app. Again, once we actually give it enough time to JIT, then things start to improve here. And this one we also threw OpenJ9 at it, since it has a feature similar to appcds, but that can also save some JIT code. We got some gains here, but again, it's saving code that's JITted, and most of our bytecode is cold. So we need to basically, like, we're talking to some of the OpenJ9 folks, we're going to tell it to try and pre-compile those script bodies as well. Then maybe we can launch into almost all native code for all of our scripts. That'll be the next experiment to try. And what's this? The last one is Rails console. Again, the Rails console, most of the Rails commands are kind of a worst case because not only do they run very short, but usually it launches JRuby twice. It launches it once to determine a set of dependency paths, and then relaunches with just those paths to isolate it from other libraries and whatnot. So here, --dev, a little bit of a gain from appcds here. More so with the serialization, which is weird. This is the class cache, again, slower than normal. class cache with appcds, now looking, that's the best. But oddly enough, in this case, if we only cached the classes that were used for that parent process, the launch process that went and dug out all those dependencies, that ends up being the fastest of all now. So there is enough in that top process that warms up and gets going that we trim off quite a bit of time there.
Kind of makes me want to profile which things are actually
that'll be the next thing. It's
hot, and then only class cast those.
It's very difficult for us to profile what's hot in the Ruby code because we see either the methods we've JITted or JRuby interpreter, and it doesn't really tell us like what of Ruby is executing in the interpreter. Okay, so on to some futures. We'll be able to wrap up pretty quick here. So now, of course, native compilation is cool again. I feel like maybe we need to get GCJ out of mothballs, and everyone will be thrilled about it. So we are experimenting with the interesting uses of native compilation in GraalVM at this point. This is early days. This is still a future work, but we've got some proof of concepts here. So first of all, talking about, I mentioned Truffle Ruby before. Truffle Ruby does usually run out of a native image. So they've compiled all of Truffle Ruby's implementation logic down, and some of their internal class logic. So they do actually pretty well on getting this base startup. Here's us with our best flag, -- dev. There is Truffle Ruby on the JVM, not with the native compilation. And here it is with native compile. But there's more to this than meets the eye. They're also actually preloading all of Ruby gems and saving that in the native image, so it's already booted. They're not actually loading all of the code that we load, so it's not quite apples to apples here. They're essentially doing like a CRIU, like a restore of where they were at 0, so that they can launch right to 0. If we make them do a little bit more work, so here we have two different ones, gem version, which would be very lightweight, but forces all of Ruby gems to load, and then of course a gem list of a large number of gems. Here's JRuby versus Truffle Ruby, JVM and native. They're 2 to 3 times slower than us, usually for just a basic gem command. And then it continues to get worse the more work they have to do. They're still essentially running cold because all of that Ruby code goes through the same sort of process it does with JRuby. So what we want to do, we've already been able to compile all of JRuby itself to native and get it to run and boot up. But there are a lot of limitations. Have to turn off invoke dynamic. We can't do any runtime JIT. We can't dynamically load any classes or libraries. So the ultimate goal then is to compile JRuby and all of those ahead of time compiled Ruby scripts down to native. And so this would be the first real, fully functional native compile for a Ruby application that leaves nothing but native code behind. So that's coming up. What we have right now is compiling JRuby down to a native executable. So here is our CRuby startup for the basic thing, the basic -E1, JRuby on JDK8. Here is after we've let it JIT, and there's where we get if we compile JRuby down. So this is at least getting us to 0 as fast as Truffle Ruby, without being Truffle and without doing all of the other tricks. But we want to be able to do this and have all the Ruby code loaded up. So that's the next thing. So futures for this, like I said, we needed the bytecode AOT to be working, and now it is. So we'll be expanding that native compile proof of concept to do the entire application, probably starting with just smaller services and command line tools at first. Also have some ideas for static optimization that we can get some profile information from the Ruby code, and for monomorphic call sites, just compile into our ahead of time bytecode a guess that it's probably the same method it was last time you ran it. And then ideally the native image compile could see through some of that and probably get a lot of the inlining that we want out of it. Most calls are monomorphic in Ruby applications anyway. All right, and the last item.
So in working with IR serialization, because we hadn't touched that in quite a long time, we started thinking about ways that we could actually speed things up. And like one big problem we have is our Ruby parsers, like it's an LR grammar with like 170,000 like states. So it takes a long time to warm up. but what if we could do something that was a bit simpler, something that could fit into a single method? So in looking at typical Ruby files and libraries, there's usually a couple requires, which are it's just a function call, and there's some modules and classes defined, and they're reasonably simple. So what if we limit a Ruby interpreter to only those things? And if the Ruby has more complicated things, like it has if conditionals inside of a module body, then we'll just use the current serialization. But if it doesn't, we'll use this new interpreter that is basically just going to be a single static method that's only going to have a limited number of instructions, and we'll go with that. I realize that all the stuff that I'm talking about here are things that will only execute once. So we have no need to have IR at all. So that was something I realized after that slide.
Yeah.
So this is a typical structure of a Ruby source, and on the right's just a little napkin thing. It'll probably just be 5 or 7 case switches with inline bodies for just standing up a new module and a new class.
Right.
It also has another benefit, which is that when we normally interpret stuff in IR, we go through this prologue and epilogue of executing the script body and then executing the class and then so forth. But in this case, it's all going to happen in the same context.
Right, and we can at least see that there are no other calls, no unrecognized calls like we got require, we've got some visibility changes, but we can basically store the structure and just run through it quickly, saving the entire Ruby context that we would normally need to execute in. So wrapping up here, precompiling to bytecode works, but it generally is hurting startup right now. Clearly a prerequisite for doing a native compile, so that'll be the next step to try that out. The class sharing features are looking very good these days. Running app CDS on JDK 13 is probably the fastest startup for JRuby at the moment. We're going to continue playing with mixing these different options together, but CDS looks good. The share classes, quick start stuff on OpenJ9 is also fairly competitive there. We're looking to try out, say, Ready Now. I think it was the Alibaba folks are working on saving JIT stuff in the background as well on OpenJDK, so we're interested in that possibility as well. Lazier and lighter IR. Really the best things we can do right now is just do less work at boot. And try to get you to a running application quicker. It's really just that first response. If the whole application, or the whole run takes 20 seconds, just getting you to the first output of it makes people feel so much better. It's that sitting there staring at a blank command line with it just doing nothing while we boot up. That's what really bothers people. Some people have suggested we should have a splash screen every time we run a command so that they know we are going, trust me.
We still occasionally get that with Java 9 Plus with module warnings.
Yeah, exactly. We got a progress bar, maybe, like starting up, yeah. But, if we can do less and get people at least some output right away, that would be better. And the native compile stuff is really cool. It shows a lot of promise, but it's really super limited right now. It's not Java in the way we know it. I think we can get small Ruby applications to compile completely down to a native binary. Hopefully that binary is smaller than 1 gigabyte once we get there. But we're going to continue to play with it and see how much we can actually squeeze out of all of these different options. And that's what we got. Thank you.
Phew. Told you it would be good.
How long does it take to compile JRuby native?
To compile JRuby native, it wasn't terribly long. in the order of a few minutes, I guess it was. Our code base isn't that large, and I also I had to strip out like our bytecode compiler, anything that would reference stuff that the native image does not like. I basically just removed it. So it cut JRuby down to essentially parser, compiler, interpreter, and some of our core classes. So it's 5 minutes maybe. Yeah. It wasn't too bad. It's not something that we would say, oh, this is part of your dev cycle now. Now that you've updated your libraries, do a native compile. Now, it'd be more like we would pre-compile JRuby plus some key libraries and then compile our interpreter in so that you'd continue to use the interpreter, but you'd get the fast startup of basic things. So a partial solution there. Or if you're going to production, compile your whole microservice down or something.
Hello. So my question is, a few years ago, we talked about this on Twitter, that you still, at the time, JRuby still defaulted to have compile.invoke dynamic set to false. So by default, without --dev, JRuby would avoid invoke dynamic. Do you think some of this could be used as an enabler to also have that on as default and not have as big as a penalty as in the past?
Right. So trying to get closer to having invoke dynamic on all the time. We've moved that bar a little bit over time. So things that are literal values, well, now they're sort of like a constant dynamic sort of thing. They boot up and then they cache a constant using invoke dynamic. That's always on, and that's what I had to kind of remove from the compiler. The real problem with us using invoke dynamic all the time is that we get those long chains of totally dynamically constructed Lambda forms. It's not something in a constant pool. It's not something we can represent as an expression there easily. So those would always still be slow. It's possible that with const dynamic or something like that, we might be able to say, here is the shape of a Ruby method call chain, cache these, and then stick this direct method handle on the end and save some of that effort. But we do so much of this programmatic building of large method handle chains. Well, that's where most of the problem is.
There are two other things. One is that Charlie just recently changed our bytecode generator so that you can decouple whether Indy's on for everything or not.
Right,
so,
sliding scale more now, so we can adjust that.
So we might be able to actually emit less Indy in places where it probably doesn't matter. But then the second thing, we've been trying to add a timing metric in to change our JIT heuristics so that we're actually JITting less code. And that should enable us to, if we truly make it to a place where we can know that something's hot, we can just use tons of invoke dynamic in that. But if it doesn't hit that threshold, then maybe we do an Indy-free compilation.
Right. Well, we're kind of building this tiered VM on top of another tiered VM. We've even talked about like, oh, we could use Indy, but maybe use really simple call sites that just basically do a virtual dispatch to some function object. That would be very quick to bootstrap, and then add a counter into the method handle chain, and then once it gets really hot, we go back and we make it an optimized invoke dynamic. I mean, there's lots of different things we can try with this, but there's only so many hours in the day.
When you tried all the app CDS things and so on, did you also try the OpenJDK AOT thing?
JAOTC. Yeah, we have played with it, and it was similar to what we saw out of app CDS and other stuff. It basically got our zero flag startup pretty close to the dev, the C1 performance, which is about what we expect. We hope for a little bit more because we wanted those bodies of code to actually also compile. It just turns out to be such a tremendous amount of code that we end up loading into the system at that point. I think we lose it there. It creates a gigantic executable for all the stuff that we actually would need to run at startup. So we need to just figure out how to make that startup stuff as lightweight as possible and only do the real hard work for methods and blocks.
There's a question for me. Clearly you know in some detail which methods are going to be hot. If you could drive the hotspot JIT compiler from a script, say, to say, compile these methods now, inline these methods into them, would you be able to get a better performance that way?
Well, I would say almost none of this affects our peak performance in general. We're already getting good inlining through invoke dynamic call sites. It just takes a long time. What it would do, and what the pre-booting bytecode and what that would do, was we might be able to hint and get warm-up curve a lot lower. Because we're confusing the hell out of the JVM. We run this code for a long time in the interpreter, and then we're like, oh no, it's not the interpreter anymore, and now it's going to be this version of the bytecode. Oh, and now we're going to re-optimize that bytecode and change it again. But if we could give some hints to the VM, it would certainly help us shorten that curve.
There is a sort of mechanism that will do that in the shape of the CI replay data that engineers use to debug the JIT.
Yeah, yeah.
It's a serialized form that tells it exactly which methods to JIT and exactly where to inline everything and exactly what all the branch probabilities are.
Yep.
You
That
can
would be
feed
great.
it with all that if you want.
Right, and we have a profiling inliner for the IR already, so it's possible we'd be able to take our interpreter profile data, feed it into a tool like that, and then say, hey, we already know this stuff, don't start from zero again.
Yeah.
Both our parser and our IR interpreter are just Java. If we could just force that to C2 immediately.
Yeah, right.
You can use the white box API
Okay.
to put stuff. To take
All
the
right.
metadata and insert it.
Yeah,
It works.
We'll give it a shot then. Anything else? Anybody want to get dinner?
On top of
Oh, there
that, compile queue is not a FIFO. There's an algorithm behind how methods are being selected. So in your case, since you care so much about the warm-up curve, it's worth visiting how in which order methods get compiled, and this might impact your warm-up curve. The way to effectively is like whitebox API. The replay file can help you there.
Sure.
By tweaking some indices, things like that.
Sure. All right. Thank you. We'll definitely do that.
Thank you. Thank you very much. That was fascinating. I think we should wrap up at that point.
All right.
Thank you.
Thank you.